It's an honor to be the first speaker of the refereed papers today. Thank you very much for coming. I'm going to make this efficient because I have a lot to tell you. For the amusement of the Chinese speakers in the room, I'm going to make one attempt at pronouncing this the Chinese way. The rest of the time I'm going to do it the naive way. Okay, it's going to be, this is about Flip Feng Shui, hammering a needle in the software stack. It's a new kind of exploitation technique that I want to tell you about, structure even. Okay, here we go. What can we do with this? An example attack that we're going to show you is a compromise of an OpenSSH server. We're going to be able to generate our own new private key corresponding to the public key that's on the server and be able to log in using our own private key, a newly generated private key. We're going to be able to force GPG signatures and thereby completely compromise the apt-get package management widely deployed on Debian and Ubuntu by forging GPG signatures. All of this we can do without relying on a software bug. There are no bugs present in OpenSSH and GPG that we rely on. We rely on very weak assumptions that make this attack very practical. There's going to be a demo of the second attack that I'm going to be happy to show you. The scientific contribution as we see it is that Flip Feng Shui is an exploitation structure that depends on two different things. One is a hardware glitch and one is a memory massaging primitive. The hardware glitch is we use to corrupt memory, but of course hardware glitches are generally speaking unreliable, they're noisy, they're non-deterministic, but using this memory massaging primitive we can make this not only reliable but also precisely aimed. We have actually, it's a little bit of a teaser, we have another paper that's been accepted that, that also employs this exploitation structure, but in a different way. For Flip Feng Shui, I'm going to show you how it works with Rowhammer and memory deduplication. Rowhammer is the memory, is the hardware glitch, and memory deduplication is the physical memory massaging primitive. We have another paper that's going to be accepted, that also relies on memory massaging technique and Rowhammer, but it's very different. So that's just a teaser to show you the generality of this. So in this talk, I'll give you an example of how it works using Rowhammer and memory deduplication. So if we, the outline of this talk is if we forget for a moment how it works, what can you do with Flip Feng Shui? Now we want to know how it works. How does it work exactly? What are the mechanics that go into Flip Feng Shui and what techniques does it rely on? What has to come together for this to work? What are the assumptions? Once you have that in place, let's show some example attacks. One is an OpenSSH attack I was just talking about. One is the GnuPG updates attack. I'm going to show you a video demo. And finally, I'm going to tell you a little bit about the real-world impact this work has had in terms of notification and what we think the takeaway conclusion should be from this work. And of course, where you can follow up with us if you want to know more about it. Okay, Flip Feng Shui at work. If you have this primitive in place, what can you do with it? So the example scenario that we are assuming is that we are co-hosted VMs with a victim and an attacker co-hosted on the same Linux host. We're using Linux and KVM in these examples, but we don't rely on it being Linux, and we don't rely on it being KVM, but they're an example environment in which it works. We assume also that, so what you'll be able to do if you employ Flip Feng Shui is that if you're an attacker VM co-hosted with a victim and you know the content of a memory page in your victim VM, you're going to be able to flip one bit in that page, in that memory page of the victim. So it may be an interesting exercise, a mental exercise now. If you want to subvert the security of a victim VM, which single bit would you flip? What's the most security sensitive, most powerful bit to flip if you're able to choose anyone in a page that you can guess the contents of? So this is the origin of the name Flip Feng Shui. We call it Flip because we flip one bit, and we call it Feng Shui because it has the memory that we are attacking has to be organized in this way to make it reliable and deterministic. Hence, Shui as in the harmonious organization of objects, I believe. So, using this scheme, we can completely circumvent the strongest possible isolation that's currently provided by modern CPUs, which is hardware virtualization. Okay, so that started the top-level view of what can you do with Flip Feng Shui. Flip one bit in a co-hosted victim VM if you know the contents of the page. How does it work? So, for this example, we assume that we're co-hosted VMs. We assume that memory deduplication is turned on in the host in Linux. It's, the implementation there is called KSM, kernel same page merging. We assume that we can use Rowhammer, and I'm going to show you a little bit about some details of RSA, which we need for the example attacks, not for Flip Feng Shui itself, but for the example application attacks that we do. We assume that, so we assume memory deduplication is on and that Rowhammer works. These are very realistic assumptions. So that's what I meant by weak assumptions. 80% of DDR3 RAM modules are susceptible to Rowhammer. Memory deduplication is commonly turned on in cloud hosting providers because they can then fit more virtual machines on the same physical machine. So number one, memory deduplication. So the green block indicates a victim VM, the red block indicates an attacker VM. The arrows indicate mapping, so virtual memory mapping from this virtual address space to a physical address space. So this normally, if you're an attacker and you're a victim, you're both in a KVM, you both have your own set of physical memory that you're about to use, that's mapped to physical memory. And the attacker has a set of physical memory, the victim has a set of physical memory, and never the twain shall meet. You know, you can never, the isolation is just because the MMU maps your set to one page and the other set to the other pages, and you can't touch. But if memory duplication is on, there's an OS feature to save memory. That means that every page, all pages that have identical contents can be merged into a single physical page and then mapped multiple times. So imagine I'm storing a copy of the Mona Lisa and the victim is storing a copy of the Mona Lisa. I'm the attacker, of course, in this scenario. And we both have a copy of the Mona Lisa in physical memory. Then the kernel same page merging will notice this, merge it to a single copy, and map it twice to the same copy. So that saves one page of memory. This can happen many times. So this is a way that you can save quite a lot of memory if you're a cloud host. Now, if the attacker goes and defaces the Mona Lisa by putting a mustache on her, right, of course, you have to reduplicate this page again. The pages are mapped copy on write, so that as soon as this write happens, this will trap to the operating system. The operating system will allocate a new page and reduplicate the page, that the defacement only happens in the copy of the attacker and not in the victim. So this makes it not only semantically sound, but of course also would be a security disaster if this were any other way. Now, Rowhammer is a glitch that happens in many DDR3 RAM modules, at least. And it relies on the fact that whenever you access a row in memory, so you see this row of cells, I-1, the charge has to come out of that row and be put into the row buffer. Now, that row is recharged, of course, so the contents don't leak. But in DRAM, also, the neighboring rows are going to leak a little bit of charge. And if that happens fast enough, if we store a copy of the Mona Lisa in row I, in the center row, in the victim row, so to speak, the charge will leak out of it slowly but surely, Sometimes this will hit, and sometimes so much charge will leak that a bit will flip, and the Mona Lisa has this awful defacement. Who would do this to the Mona Lisa? It's really outrage, really, oh my God. So what, earlier in this earlier example, we had a mustache on the Mona Lisa, so there could be. And the effect of Rowhammer depends on which parts of physical memory you access. If you access one part of physical memory, you get a flip here. If you access another part, we get a flip there. We call this templating because we're looking for where can we flip bits. It's very hardware dependent. So we have to test this out to make it reliable. So if we do another part of physical memory, then what happens? We do read, and then we get this. Another bit flips, and then we get this defacement of the Mona Lisa, which is also an outrage. But we're looking for the mustache, so we try another piece of physical memory, and then we read, and then we get a mustache. We get a third flip. We know we have to use that piece of physical memory to get a mustache on the Mona Lisa. Normally, in normal operation, you won't see this very often because the CPU will cache all this data, so the reads won't happen from the same DRAM. But if the DRAM is hit repeatedly in the same way, that's how the Rowhammer can happen. Now, put the two together, and then you start to see how Flip Feng Shui works. I've written a copy of the Mona Lisa as an attacker in my VM memory. The victim has written a copy of the Mona Lisa in their memory. The operating system has noticed this is the same content, so at the physical level it's going to merge the two and map both copies into the physical page, to the same physical page. As an attacker, I can make sure that the victim uses my physical memory. We exploit properties of Linux KSM to do this. And that means that if I do Rowhammer in the attacker VM, the same change that happened before with the bit flip will happen again with this page, So, and that's how we can control the location and control the reliability of Rowhammer by performing Rowhammer in the attacker. Now we get the mustache that we wanted. It will also happen in physical memory, and therefore also in the victim. So significantly, this breaks copy on write. It doesn't happen to the CPU, so it's not trapped, it's not duplicated, and therefore this change will propagate, and the isolation between VMs is broken. So, okay, properties of RSA, which has nothing to do with Flip Feng Shui, but does have something to do with the example attacks. Two example attacks we're going to show you are OpenSSH and GPG. And these attacks do rely on properties of RSA to make this work. RSA is just to reiterate very briefly, RSA is a public key crypto system. That means it's very convenient, because if you encrypt a message with a public key, you have to decrypt that with the private key. You have to decrypt the ciphertext with the private key. That means the encryption key can be public, hence the name, right? You don't have this key distribution problem anymore. The private key you have to keep private, because that's what can decrypt your messages. That's also what can sign messages, and anyone who has the public key can verify the signature. Now, the properties of RSA depend on the factorization of the so-called modulus in RSA. Modulus is part of the public key. All its arithmetic of RSA happens modulo a very big modulus, 2,000 bits, 4,000 bits. And you compute the private key by knowing the factorization of the public key. Now, when you generate key pairs, that happens by construction. You generate two very big primes, you multiply them, that's the public key, and because you know the factorization, those two primes, you can generate the private key. Then you throw out the factorization, the public key becomes public, and nobody can generate the private key, because you can never factorize such a huge number, if you're not the NSA, of 2,000 bits. But if you corrupt this modulus, then it becomes just another number. Then you get just another random factorization, and it turns out oftentimes it's very easy to factorize a 2,000-bit number if it's not so carefully constructed. And this graph indicates that. If you have 50 possible variants of an RSA modulus, the middle line of 2,000 bits, this is an example of the SSH key size. If we have 50 variants, we call them templates, 50 locations that you can flip a bit, then if you have 50 of them, and 50 is not many, you know, within a page, then you're practically sure that you can factorize it within an hour. And in practice, we've seen it really just takes a few minutes to find a flip that you can factorize the modulus of, and thereby generate the corresponding private key, because just to take a step back, that's what we're trying to do here. We're trying to change the public key that someone trusts to authenticate something. We're changing it and then generating a private key so that we can fake that authentication, because it's going to trust the modified private key, a public key. Okay, so just to recap, we are able now, using this technique, Flip Feng Shui, to corrupt a public key that someone's trusting to verify signatures, and generate a corresponding private key so we can fake signatures and we can fake the SSH authentication. This authorized keys file, SSH has many kind of authentication systems. One of the most common one is a password, or maybe nowadays the most common one is the RSA key system. If you generate an SSH key pair, you generate public key and private key. Public key doesn't have to be kept secret by the very beautiful nature of RSA. So this thing here is a base 64 encoding of a RSA public key. Now, if you put that text in your home directory, in your authorized keys file, and you can prove to the SSH server that you have the corresponding private key, you can log in because you proved your identity. You're the only person who has the private key, right? Thank you for nodding, sir. And that's what you can see where this is going, right? If we can flip one of these bits and the base 64 decoding corresponds to a new modulus and we can compute the corresponding private key, the SSH server is going to let us in. It's according to the rules. There's no bug at play here. So how does this work then? We write authorized keys files in the attacker memory, because we could guess this, right? We can go to, as an example, because authorized keys files by the design of this whole system are not to be kept secret. We can go to GitHub. GitHub publishes all SSH public keys that users upload to them to authenticate themselves with, because it's safe, it's supposed to be safe. So the attacker writes these authorized keys files in memory. We then rely on the host to merge these two things into physical memory. We find a flip that will properly decode to a new module that we can factorize, and that means we can generate a new private key. It looks like this. That will mean, of course, it also happens in physical memory, because that's where stuff is stored, and therefore it happens in the victim, and that will let us log in with our newly generated private key. Just to give you an idea of how reliable and how fast this is, this is a CDF of a combination of 300 iterated attacks that we did. You can see that by 6 minutes, more than half of them were done. By 12 minutes, all of the successful were done. 84% were successful the first time. If we try again, we'll get over 95% reliability. Okay, this next one is also an example attack. It's an attack that relies on apt. So apt is this package management system widely deployed in Debian and derivatives like Ubuntu. And it authenticates its packages using GPG signatures. It relies on sources.list to find out where packages are to be retrieved. And it relies on trusted.gpg, this keyring of GPG public keys that it allows to authenticate packages, their authenticity and their integrity when they are downloaded. Now, if the GnuPG updates attack that we subvert this authentication system with, this authorization system, is that we do 2-bit flips instead of 1. One is in the sources.list file so that we can change the domain name in, say, ubuntu.com to ubuntu.com. You know, this happened in our example attack. So that means that the victim will go to our malicious repository hosted at ubuntu.com. We have this domain, by the way, and we have more of these domains, and they are for sale to interested parties. See me after the talk, and you know, first come, first serve. And that means that this totally legitimately, this victim will go to our malicious repository, you know, and we're not playing any fine tricks with DNS or messing around with network traffic like that. We're just saying this is the place you go to, and then the victim goes to there. Then trusted, and if you flip a bit in trusted.gpg, that means the modulus of that public key that it trusts to generate or verify, signatures of real authentic packages also changes. And if we can factorize that public key modulus and generate a new corresponding private key, then we can not even fake, we create signatures, totally authentic signatures with a new private key that the new public key that's changed will verify against. Now these keys are 4,000 bits, so it's a little bit harder than with SSH. You know, we can only do 5%, but still that's more than enough bit flips to make this attack work realistically. We rely only on information that's part of a stock Ubuntu or Debian install, right? Source.list and trust.gpg are not expected to be very different over different installs. So these assumptions are even weaker, you might say. Now I have a video demo of this happening. I have a video demo of this happening. I'm going to show you some about it now. And this video, the whole attack happens in 20 minutes. It's heavily cut just to show the interesting bits because there are long periods of rowhammering and deduplication. I'm going to talk over it to show you what's going on. I hope you can read the text. If not, I'll read it out. Okay. Now, this video is going to show you X terms. X terms are going to appear here and here and here and here and here. And we're going to boot the VMs, our attacker and the victim. Now here is the victim. This victim is just doing totally normal apt get update and an apt get upgrade, okay? All right. So first we're going to change the location of source.list. This is happening on the left. We're doing rowhammer here. We're doing rowhammer here. And this makes us change the location from where we get the repository list. And as soon as we found this bit flip, we're going to send the attacker to a malicious repository. Here is our malicious repository. No activities happened there yet because this bit flip hasn't happened yet. So let me show you what happens when that bit flip is found. We wait for the deduplication to happen. That bit has flipped. Now, if the victim does a visit to the malicious repository again, we're going to show you that's going to happen now. We do another update. And now we see activity on our malicious repository. And we're also going to do an upgrade. But wait, the signature isn't verified, right? The GPT is saying, no, we can't install this package because it's not signed. It's not signed by any key that we trust. If we do an upgrade, no upgrades happen. So now we have to bit flip a flip in the GPG keyring. So we have to change the public key in GPG so that the corresponding private key that we've pre-computed is going to be trusted. It's going to start to be trusted. So will that happen in time for this presentation to end? Who knows? Oh, the bit is flipped, so now we can use a new private key that we've generated to sign this New malicious package. We're going to backdoor, see, we're going to backdoor core utils. We're going to sign it. We're preparing the repository. Oh my goodness. If we're going to do an update now, what's going to happen? Which package are we going to infect? Core utils. What happens? But first, how does ls normally work? ls normally works like this. Now what happens when we do the update? Is it going to work? Is it going to accept the key? Is it going to accept the signature? Yes, it's going to accept the signature. ls is backdoored. Thank you very much. No bugs. Okay, what has happened with this work since then? We have cooperated with the Dutch National Cybersecurity Center to do disclosure and notification on this problem, so that all this work has been kept private until today. The NCSC has coordinated with other cybersecurity centers in other countries and notified affected parties of this work. So they've notified Red Hat, Oracle, Zen, VMware. Those are hypervisor vendors that could be interested to know this ahead of time. Also notified Debian, Ubuntu, and also the maintainers of OpenSSH and GnuPG. So you can see sort of this is the range of the software stack that are affected by this and could potentially mitigate this problem. So all of these have been notified, and all of them have given an appropriate response. Also, some hosting companies have been notified by the NCSC. The NCSC put together a fact sheet, which is available on their site now about, be careful about virtualization. And GnuPG has already made a commit that mitigates this problem for their specific application and put that in mainline. NCSC has done an extremely professional job of this, by the way. We're grateful to them to make this this disclosure of this information very safe. So what is the conclusion? We conclude that Flip Feng Shui is capable of breaking an extremely powerful isolation system. The hardware virtualization provided by the CPU is the strongest possible currently there, but Flip Feng Shui breaks this isolation. It was already widely known that co-hosting VMs is a risky proposition because of all kinds of side channels. We've got cache attacks, we've got dedupe attacks, and so on. But this dedupe attack, don't forget, it's not about leaking information, it's about writing information. So this is the first attack, as far as we know, that actually uses deduplication not as an information leaking vector, but as an information manipulation vector. Now, the most straightforward mitigation that we see is simply disable memory deduplication on machines that have mutually untrusting VMs or other parties on it. So, if you'd like more information about this work, please go to this project page or follow up with me or this team with coffee, in my case. Thank you for your attention.
It's a really cool attack. So we have time for a few questions. I guess to get started, maybe I'll ask a question first. So you gave an example of an attack on RSA. And it sounds like you could also do an attack like this on elliptic curve Diffie-Hellman type systems, where you change the curve that you're on.
That's a very good question. For Diffie-Hellman, that was actually the first thing we wanted to try, but we found that so Diffie-Hellman, as you may or may not know, relies on the difficulty not of factorizing, but of the discrete log problem. Now, but the algorithms for solving this discrete log problem, even if you know the factorization of the group modulus, are less sophisticated, I would say, or less accessible to non-cryptographers, maybe. So that needs that becomes much harder, much faster, given the same modulus as far as we've investigated so far. We do think we definitely know this is possible. We know how to do it. But that's something we haven't worked out totally, and it seems like all other factors being equal, it's harder with the same modulus size.
Actually, maybe just as a suggestion, if you look at elliptic curve Diffie-Hellman, if you change the elliptic curve equation, you get a curve that's not prime, and then you can do the attack. So
can we talk about that? Because I would love to hear how that works.
Yeah, please. Other questions.
How do you ensure page alignment to force deduplication of, for instance, the authorized keys file?
Okay, great question. That's we rely on the fact that the authorized keys file, and part of the reason that we use VMs for this, apart from demonstrating this very strong isolation to be broken, this authorized keys file is in the page cache of the victim VM. So it's not hanging about in memory. Well, it also is hanging about in memory, but it's also going to be in the page cache of the victim. So as soon as that thing is in memory and we flip it in the page cache, then all future reads of that during authentication will come from the page cache and therefore be the flipped version. Is that a satisfactory answer to your question?
Yes, thank you.
Ben, amazing talk. Brilliant result, brilliant presentation.
Thank you very much.
I'm a cloud client. I'm not a cloud provider. I'm really worried about my VM with SSH in it. What can I do? I'm asking my cloud provider to turn on the duplication. They're thinking about it. What can I do today?
Okay, that's a great question. If you ask your cloud provider to turn off the duplication, and did you say they were dicks about it?
Thinking about it, but
oh, you were thinking about it. Okay, sorry. Okay, right. Pardon me. Okay, I just assumed that that would be the answer. Well, they will do this as a cost-saving measure. So you'll force them sort of into different state space of their business, and it means either the price is going to have to go up if they want to do the effort at all, or they won't do it at all. So yeah, so what I think cloud providers, the kind of thing cloud providers should offer, I think, is to host machines, is to offer the fact, well, either you get what you pay for, which is then less, or maybe there's a more expensive option which says, well, we guarantee you one machine on which you host all of your VMs or something like that, so that there are security boundaries on the same physical hardware.
They're not going to do that.
That proves the relevance of this work.
Okay. So
actually, maybe it would make sense to add error correction in software.
Yeah.
So error correction to memory in software.
Looks like if I just shard the key, you change the format of the authorized keys file to add a little hash on it. You fixed at least this one.
Absolutely. So there are on these applications, there are going to be lots of application level mitigations. The OpenSSH guys, we've told the OpenSSH guys about this, and well, yeah, I guess I can say it. They said, no, we don't think this is realistic. The GnuPG guys have said this, or actually, to be perfectly honest, they said, we don't feel like it's sort of our job to fix this, right? They think just, well, it would be a very simple mitigation for them, but I think they said the lower levels which are causing this problem should fix this. GnuPG had a more productive response, but of course that doesn't solve the general problem. You could solve the general problem, we think, at an OS level, but that has all kinds of performance trade-offs. Either you waste a lot of memory, because that means you can separate sort of the Rowhammer boundaries. You can separate that so that mutually untrusting parties cannot find you with Rowhammer, but that means you have to either waste a lot of memory or partition the memory, something like that. That's going to be possible, but there's sort of no way out of it without sacrificing something.
Okay, thank you.
Thank you.
Great, thanks a lot. This is a really good talk. Really
Great.
nice results.
Thank you, everyone.